24, we're asked to determine the acceleration after 3 seconds. So a of 3, can anyone find a of 3 for us?
18 minus 24.
18 minus 24, which is -6. Measurement unit.
Meter per second. Oh, it's going to be meter.
Feet per second squared.
Feet per second squared. Very good. Do not confuse with the acceleration, which is feet per second, because this is the rate of change of the velocity with respect to time. Feet over second over second. Okay, perfect. Okay, this is the last question is very important. Let me write it for you. Part H. I don't want you to think that I'm skipping anything. It says graph with a graphing calculator. So we can graph the distance, the velocity, and the acceleration, and there is a calculator sign next to it. Okay, final question, part I. When is the particle speeding up? Slowing down. Okay. The next table, like all the tables that I show you, please try to understand them and try to use them unless you want to invent your own. That is better, which I'm fine with it. But the summary that we, and the table that we're going to use the entire semester, it's extremely important. Okay, so back to T. And we are talking about 0 to 8. Does it say that? But we are talking about 0 to 8 now. Okay, so we have V of t. We have A of t. And we have conclusion. We have 2. We have 6. We have 0. We have 0. You already told me this. This is carved in stone now. We have the acceleration, 60 minus 24. I need to know where this acceleration is 0. And it turns out that at 4 seconds. So 4 will be in the table as well. 0 in the row for acceleration because at 4 is 0. And I need to determine the sign to the left and the sign to the right. Can anyone tell us this is the acceleration here? Can anyone tell us the sign to the left of 4 and the sign to the left of to the right of 4?
Is it negative and positive?
Right. We don't have to think. Here's why. This is a linear function with a positive slope. A linear function with a positive slope looks like this. It must come from negative infinity and go to positive infinity. We don't have to think. If the leading coefficient is negative, then the slope is negative. In other words, it's coming from positive values and goes to negative values. So for the linear functions, we always think in these terms. We don't have to spend our time plugging in. Good. Okay, and now I would like to explain what's happening here. As you see, there are several intervals. This is an interval in which the velocity is positive and the acceleration is negative, which means that this is the velocity force and this is the acceleration force. They're working against each other. They are not going in the same direction, helping one another. One is going this way, the other one is going that way. Do you think that the particle is speeding up or slowing down?
Slowing down.
Right, of course. So slowing down. Here's, both of them are negative. So now this is the direction. They are going in the same direction. It's like the airplane and the tailwind. It's getting the help. They're helping one another to increase the speed. So both negative, they are helping each other. They are working towards the same target. So speeding up. What happens here? When the velocity is negative and the acceleration is positive? Between 4 and 6.
Slowing down.
Slowing down, and again, this time they are both going in the positive direction, so they are speeding up. So this is again like I ride my bike and I have a headwind. Well, I'm much slower than I should be because there is a force against me. Any questions on this? Any questions? Any questions? There is another type of problem and that I would like to discuss, but instead of discussing it now, I would like to move that problem and connect it to section 3.10. So 3.10, hopefully today, we're going to talk about marginal cost. It really does not, this type of problem doesn't really belong here in 3.7. We're going to talk about it in 3.10, and I will not forget to come back to it. Okay, we do not cover section 3.8 in this class because it's part of pre-calculus and college algebra. 3.9, I need more time for it. So I think I'm going to use the entire time on Thursday. So today I'm going to finish up 3.11 and 3.10, hopefully. I'm going to jump to 3.11. I did not forget that that's the correct order in WebAssign. And in 3.11, we are going to talk about hyperbolic functions. Hyperbolic functions. Okay. What are these? Do we really need more functions? Don't we have enough? Well, here's a very nice picture in the book. I have never been to St. Louis, but I hope you can see the arch. I have never been, as I said, but this is made using a hyperbolic cosine function. Another use of the hyperbolic functions, here is another one. As you see, these are poles, let's say potentially telephone poles. The cable that stretches between the top of one till the top of the other was calculated, the length was calculated using a hyperbolic cosine function. The ocean waves, the same, hyperbolic functions. Okay, let me just list them. They have sine, cosine, tangent in them, but they are not trig functions. They are not trig functions. So hyperbolic sine is e to the x minus e to negative x divided by 2. So why is this a function? So this is a function that has exponential functions in it. Where's the connection to hyperbolic sine? Why can't we name this something else? Why did we have to use sine? There's no sine here. There's a difference of two exponential functions. How did we come up with this? I'll show you in a minute. Hyperbolic cosine is the same thing but with plus. Hyperbolic tangent is the same thing, but it's the ratio of these two. So it's e to the x minus e to negative x over e to the x plus e to negative x. Of course, hyperbolic sine divided by hyperbolic cosine. The answer is they kind of behave like trig functions. That's why the sine and the cosine in the name. And of course, everything else is the same. Hyperbolic cotangent x is 1 divided by hyperbolic sine, and so on and so forth. Everything else is the same. I only want you to remember, and also because they have, the relationships are the same. So here they are. I'm not going to test you on this. All the formulas for hyperbolic sine x plus y, very similar to what we knew before, just minor changes in the signs. That's not, formulas will be given to you if I ever do anything with more than what I'm showing you today. So what I would like you to remember, though, is this. What they are, these three. Yes, this is very important to remember. And hyperbolic sine prime, which is hyperbolic cosine. And now even easier, hyperbolic cosine prime is also positive. Not like cosine prime would be negative sine prime, negative sine, right? But here they're both the same. And hyperbolic tangent, same thing, hyperbolic secant. That's all I'm asking. Of course, they have inverse hyperbolic functions. No, we can use tables for those. That's all I'm asking you to remember. What I would like to do is just work on a couple of problems. At the end of 311, if you'd like to choose, please tell me. Problems from, I just want to focus on differentiation. Problems 30 through 45 in 311, if you have WebAssign brought up. If not, I will choose. Let's say 33. You can choose the next. 33 in my book anyway. So h of x equals natural log of hyperbolic cosine. And we're asked to differentiate this function. Nothing different from before. H prime equals 1 over hyperbolic cosine times the inner function prime, which is not even minus, but simply positive. Sine over cosine hyperbolic is hyperbolic tangent. Feel free to choose the next one if you'd like. If not, I will choose a ratio this time.
Real fast, can you remind me the difference between parabolic and hyperbolic?
The difference between hyperbolic and?
Parabolic?
Oh, parabolic is a parabola. Or this. This is not a function. These are not functions, but this is a function. So they are conic sections.
And then what's the hyperbolic one representative of?
These graphs. Let's take a look. Very good.
Yeah, what's the shape?
Yeah, it's very similar to sine and cosine. So this one will look like sine. And this one will look like parabola. Let's take a look. Very good, very good. Let's do that. Good. So in y equals, clear, whatever you have,